Hi, I'm Edwin. I once built an AI to teach kids about gravity. I once taught critical thinking and built a teacher evaluation system in Singapore's polytechnics. I wrote 2 travel guidebooks and traveled around Asia, spinning yarns for CNN Go, now known as CNN Travel. Nowadays, I work as a digital strategist where I solve hard problems in digital advertising, like Sudoku. Now, I'm using Peter Novak's solution, depth first search with constraint propagation. It's a lovely, elegant, and remarkably fast solution as compared to the usual brute force search solutions. His algorithm comes in 3 parts. 1. Board setup. 2. Eliminate and update. 3. Search and solve. Let's use this Sudoku board as an example. In board setup, the very first part of the algorithm, every dot and number on the board represents a square. Remember the term square. We'll use it very often. Every square has peers, as you can see. There are other squares in the column, the row, and the box. And every square in general has 20 peers. Lastly, squares that do not have a value, anything else that is empty, not 4, 3, 7, can take on any value between 1 to 9. Now, that's the board setup. Part 2 is about eliminating and updating the board, which are typical strategies used in Sudoku. Now, the first strategy, eliminate. If a square has a value, then we remove it from the square's peers. For example, A1 has the value 4. So what we'll do is remove the value 4 from the row A1 to A9, from the column 1, and the box that is bounded by A1, A3, C1, C3. And we do the same for value 5 in A9. We do the same for value 8 in A7. And at the end of the day, before we even start, here's how the board looks like once we fill up the rest of the starting numbers. Now, the second strategy is quite straightforward. If one square can only have one value in the unit, be it a box, column, or row, then we use that value. We replace the square with that value. In this case, there are 3 boxes that can only have one value. I've highlighted them in red. Now, so we will replace this box with that one value. In this case, it's 4, 3, and 1. And repeat strategy 1 to remove values from their peers. Now we have a board that's good to go, and we are ready. Let's get set. And we choose one unfilled square that has the smallest set of values, right? For that, then we consider all the possible values in that square. We take one value, one possible value, and then we assign the square that value. Now, remember what we did earlier? Eliminate and update. That's what we do now. We do it for this square's peers, and we do it for the peers of the square's peers. Why? Because a small change could create a ripple effect down the line, and this is known as constraint propagation. But what if we cannot update the square's peers, or if there's a contradiction, like you're supposed to, the program tells you to remove 9, but the only value left is 9, and the Sudoku board cannot have no values, right? We backtrack, we roll back to an earlier square to try another value. Now, at this point in time, once we've eliminated the square's peers, values from the square's peers, we then choose another square to go on and carry on until the board is solved. This is known as depth first search. We stop only when all the squares have only one value each, and that is the answer. We'll move on to the program itself in a bit. Let's start. The code called solve, which sets up the board and kicks off the search program. Now, as we mentioned earlier, it looks for a square with the fewest possibilities. In this case, it's G1 with values 2 and 9. Now, we need to do constraint propagation to eliminate the value 2 from G1's peers. Here's an interesting thing that happens. It hits square G3. And what happens? It changes tack. It now starts to eliminate the value 9 from G3's peers, as you can see. That's how constraint propagation works. Any change in the environment on values will be propagated downwards to the peers, like a layer after layer after layer. But what happens when it finishes? As you can see, value 9 has been eliminated from all of G3 peers. It picks up from where it left off. In other words, in this case, it goes back up to square G7 to eliminate the value 2. Now, once all the updates are done, what happens? Let's go on. The program, again, picks the next square with the least possible number of values and carries on until it's solved. But there's a snag. And now let's fast forward to backtracking. Whoa, now there's a contradiction. We can't remove 9 from a square that only has 9 as value. Sudoku, there cannot be an empty value in the Sudoku board. So what do? We backtrack 9 levels from E2, in this case, all the way up to A5. So instead of eliminating the value 6 from A5 and its peers, what we do now is then eliminate 9 from A5's peers. And that's essentially what backtracking does. Hit a dead end, go back, try another place. And that is the premise of depth first search. After backtracking a few times, and after finding unfilled squares for a few times, we now have the answer to our Sudoku puzzle. All done from empty, from what you see earlier, to a filled puzzle where only one square has one value, done in 4.83 seconds. Fairly fast, actually. We now have the solution to Sudoku. as done up by Peter Novick. But here's a good question. Where else can we use it? I can imagine applying this solution to workforce scheduling, for example, nursing rotations in a hospital, or routing trucks, for example, helping DHL find the best way to get from one point to another point. Thank you for watching. Please check out Peter's solution. I do encourage you to do that. Links in the caption, and don't forget to like and share my video. Thank you and have a good day.